Okay, in this video we're going to walk through the actual analysis of the data in JASP. Okay, so we're going to take the same data that we had that we used to conduct the t-test by hand. So there are the raw scores and means and so forth for group 1 and group 2. And what we need to do is then set up the Excel file in a way that makes sense for JASP to do the analysis. Now what I want to draw your attention to is that I have 4 columns in the file. Each row represents data from an individual subject. Okay, the columns represent the variables. So our first column is simply a subject identifier. So each subject is given a number. This is not used in analysis. It's just used to identify subjects. The next 2 columns are variables that represent either the sex of the subject or the condition that they were assigned to. Now these are what we call dummy coded, meaning that we've assigned numbers to represent a certain status of the participant. So for sex, a 1 equals a male participant and a 2 equals a female participant. It could be just the reverse. 1 could be female, for example. It doesn't matter. But sex is dummy coded. The same is true for condition. A 1 in this case represents the experimental group, the folks who received the online communication training, and a 2 is the control group. Our dependent variable was the number of distress words that participants used in a 5-minute discussion with their partner. Now for the experimental group folks, they had gone through the online training. For the control group, nothing had changed for them. They had received no online training. And the values here correspond to the raw scores that are presented over on the right side of the screen for groups 1 and 2. You can see that the value here, 14, 13, 15, 16, right, corresponds to 14, 13, 15, 16 for group 1. Now, we're going to save this file as a CSV file, and that's the file that we will upload into JASP. So let's take a look and see how that works. So here's the file as it was uploaded. And you can see it looks pretty much exactly the same as what we saw in Excel. Now, one of the things I want to show you that is kind of cool to do in JASP is you can make these values, especially the dummy coded values, a little bit more interpretable very easily. Especially when you have a lot of variables, it's easy to forget what the values mean. And this will become useful in our output as well. So I click on the variable name, and up comes a little panel that says value 1, 2. And then the labels equal the values. Well, we want to change that. We want a value of 1 to mean a male, and we want a value of 2 to mean female. And you'll notice that that's dynamically updated within the data file. Now, JASP is still reading it as a 1 and a 2. It's just that you're seeing it as male and female. We can do the same with condition. And let's say a 1 is communication training, and a 2 is the control condition. Okay, now let's run our t-test. And we want to select independent samples t-test. So up it comes. The first thing we have to do is tell JASP how we're grouping the data. What are the groups we're interested in? Well, we're interested in comparing the means between the experimental condition and the control condition. So condition is going to be our grouping variable, and our dependent variable was distress words. Okay, and you can see JASP has already run the t-test. Okay, and that's great. We just still have to make a few more selections. Okay, and so we'll hold off on interpreting this output for just a moment. Okay, but that's a pretty cool thing that JASP does, is it automatically, shows in real time the result of your selections in this control panel. So let's go back over to the left side of the screen. You'll see we're going to run a student t-test where it says alternative hypothesis. This refers to the type of test and especially the directionality of the test that we ran. Now, we had already selected we decided to make a two-tailed test, right? A non-directional test. So the null hypothesis in a non-directional test is that the means in the population represented by the 2 samples are equal, right? And the alternative hypothesis, which is what is represented here, is that they're not equal. Okay, so we're going to click this first one, which is already selected. Now, parametric statistics have certain assumption checks. One is the assumption of normality of the underlying distribution. The other is that the variances for the two groups or samples are equal. That's the homogeneity of variance assumption. So we're going to click that as well, and we'll go back in just a second and interpret the output. Okay, let's go back up to the top. We're going to click location parameter and the 95% confidence interval. And again, we'll interpret that in just a second. And then we're going to click effect size. Now, it'd be nice if it had eta squared here, but it doesn't. So let's go with Cohen's d. So we'll click that. And then we'll also get the descriptives because we'd kind of like to see the mean for each of the groups. Okay, I'm going to skip descriptive plots. You don't really need to see that. It might be useful for you to understand the data a little bit better, but we don't report any of that really in APA format. It's more of a visual aid. So we'll just kind of skip that for now. I don't think we really need it for this example. Okay, so everything has been selected. I'm going to expand this panel just a little bit more if I can. There we go. So here's our output. Okay, and what I want to do is I want to just start from the bottom, and I'm going to check on our PowerPoint slides just to make sure everything corresponds with what we did by hand. So let's start with our descriptive statistics. And here's our dependent variable distress words. And we have two groups, right? Group 1 was the communication training group. There were 7 folks in the group. And then we had a control group also of 7 folks. Now the mean was 14.143 for the communication training group and 8.143 for the control group. So let's go back and take a look. Notice that we had 14.14 here for group 1 and 8.14 for group 2. So everything checks out so far. Okay. Now, the assumption checks, don't confuse these with the actual T ratio statistic because they have to be interpreted a little bit differently. Remember what the assumptions are for a parametric test. One is that the variances between the two groups are equal. That's important because we're pooling the variance between the two samples. So we don't want them to be different. In other words, we do not want the p-value, the probability value, to be less than 0.05. We want to be greater than 0.05. The same is true for a test of normality. We don't want deviations from normality in the data. So in order to satisfy these assumptions, okay, anytime you look at assumption checks, you would like to see values that are greater than 0.05, not less than, okay? When we actually run the t-test, we want to see values for p that are less than 0.05, and that can be kind of confusing, right? Students oftentimes confuse these different types of tests. And typically we don't go into in an undergrad stats course how these tests are actually conducted or run. So we focus just on their interpretation. And in this case, what we're noticing is that the first test, the test of equality of variances, which is Levine's test, we just look at the p-value and we notice, hey, that's greater than 0.05. And the way we interpret that is to just say, there's no reason for us at this point to think that the variances between the two groups are significantly different from one another. So that justifies and makes it okay for us to proceed with pooling the variance, which is how we actually calculate the t ratio, right? So that's good news for us, that the p-value is greater than 0.05. Same with the normality. Each of these groups then are examined to see if the underlying raw score distribution deviated from a normal distribution. The p-values are all greater than 0.05, 0.88 for the communication or training or experimental group, and 0.967 for the control group. Because those are greater than 0.05, right, we conclude that there's no evidence that the data are distributed in a way other than being normally distributed. So again, good news for us because we assume normal distributions. Okay? And that takes us up to the top table, which is the t ratio itself. Okay? Now, what I want to do is let's go back to the PowerPoint for just a second, and I'm going to sort of click through all of this good stuff, and we're going to go down to this panel where we computed the estimated standard error of the difference. Okay. Now, one of the things that you notice is this table has the t ratio, which is 3.338, rounded up is 3.34, which we already know we got. We also had decided that degrees of freedom was 12 because n was 14, and degrees of freedom is n minus 2 for a independent group t-test. The p-value is very small, 0.006, and all that means is that the probability that we would observe a difference in sample means of the size that we did by sampling error alone is less than, well, it's equal to about 6 in 1,000. So really unlikely, okay? And again, justifying us rejecting the null hypothesis. The mean difference is just the difference between the means. Where would you find that? Well, if you go to descriptives, down here at the bottom, you see that the mean for the communication training group was 14.143. For the control group was 8.143. So you subtract the control group from the communication training group in terms of those means, and the difference is 6.00. Okay? Now, so that's what we essentially get in the numerator of the calculation of the t ratio, 6.00. Right? Now, the standard error of the difference, what we were expecting on average to see in the mean difference, right, was 1.798. Now, let me just pull back our slides and say, well, where was 1.798 in our calculations? Okay, well, you'll notice when we did the estimated standard error of the difference, it came out to 1.80, right? So 1.798 rounded up is 1.80. So JASP is reporting exactly the same standard error of the difference that we had. Okay? All right. Now, what we get here is the 95% confidence interval for the mean difference. Now, the lower boundary is 2.083. The upper boundary is 9.917. So the mean difference we actually observed was 6.00, right? And what we're saying is, with this confidence interval, is that we're 95% confident that in the population, the actual mean difference falls between 2.08 and 9.917, right? So we're 95% at somewhere in there. What we actually observed in the sample was 6.00. In the population, we're 95% confident that the true population mean difference is somewhere between those two values. And then the last thing that we observe is Cohen's d, right? And Cohen's d is simply a way of expressing how far the mean for the communication training group is from the mean for the control group in standard deviation units. So this mean of 14.143 for the communication training group is actually 1.784 standard deviations away from the mean for the control group. Okay, so the average person in the communication training group was using quite a bit more distress words than the average person in the control group, and that's expressed in standard deviation units. So that's really the output, okay, that we would be interested in doing. There are other selections, that we could have chosen. For example, one kind of cool thing that you could do is you get the confidence interval for the effect size as well. So if I click that, let's see what happens. Now, Cohen's d was at 1.784, and when we do a 95% confidence interval for Cohen's d, what we're saying is, okay, in the sample we observed an effect size of 1.784. In the population, we're 95% confident that the true effect size is somewhere between 0.496 and 3.022. So what we observed in the sample was 1.784, but we're 95% confident that the Cohen's d in the population is somewhere in this range from 0.496 to 3.022. And that's pretty much it. That's pretty much the interpretation of the data. Relatively simple to run. The key is to really understand what the output tells you, okay, and be able to interpret it correctly. But it's not particularly difficult to run the analysis. You just have to, again, choose the right analysis and then understand what the numbers are communicating. And the more you practice it, the better you're going to get at it. So that's going to do it for this video. Hope you enjoyed it, and I hope that you're enjoying learning a little bit more about stats.